All right, folks, we are back for another segment of analytics for decision making. And in this segment, we're going to kind of build on what we covered in the last segment, which was valuing an imperfect signal using our three-step process for finding option value of information. We did this first by kind of starting with a perfectly informed geologist, and then we perturbed the geologist a little bit. We said, suppose he's only 75% precise, which means given that the well, there were 20 successful wet wells, he would identify 15 of them correctly, 5 of them incorrectly. Given that there were 80 failure sites, dry wells, he would get 60 of the 80 correct, but he would get 20 of the 80 incorrect. He was making a mistake 25% of the time. What we're going to do in this segment is we're going to lower the quality of the geologist's signal even more, even lower precision. In the last segment, the geologist's precision was 75%. In this segment, we're going to lower it down to 50%. And in fact, in the next optional segment, you should also be able to see that we derive the value for any value of the precision. In fact, I call it a variable parameter P. So if you plug P equals 100 in, when you get to the next segment, you'll get the perfect information case. When you plug P equals 75 in, you'll get the case from the last segment. When you plug P equals 50% in, you will get the case we're dealing with now, where the geologist makes a mistake 50% of the time. So now, again, we still have 20 wet wells and 80 dry wells, right? 20 successful sites, 80 failure sites. But the geologist makes significantly more errors. He gets half of each of them wrong, right? 10 false negatives, 40 false positives. Okay, and our goal and our process are otherwise the same. We want to figure out what is the value of the geologist report in this case. And again, in the past segments, we've computed the expected payoff with no information. We now want to do this for this imperfect signal to make the appropriate comparison. Taking the same approach and utilizing that data table in the bottom left corner of the screen and our relative frequency approach for measuring probabilities, we should be able to fairly quickly compute the associated tail conditional probabilities in red, as well as the blue unconditional probabilities for the realization of either signal outcome. Okay, from here, we're going to take exactly the same backwards approach we had before by computing the expected payoffs conditional on each signal realization and using that to characterize the optimal action given each signal realization. Okay, so assuming here that we are dealing with a good signal realization, top part of the tree, there's a 5th chance that we get 30 million, and 4/5 chance we lose 5 million, okay, which comes out to exactly 2 million. In fact, if you look at that carefully, that might look familiar. That was in fact the same calculation we did in the no information case. That's important to realize. That being said, it is always optimal to invest after receiving this good signal, even from our coin toss geologist. So if we get that good signal and we face this decision, we're investing, okay, which is what we would have done without the information anyway, right? We were investing willy-nilly, randomly digging. Okay. However, the expected profit following a bad signal is also $2 million, meaning even if the geologist tells us it's a bad drill site, do we listen to them in this case? Answer is no. And that's because their signal quality has gotten poor enough. Like imagine, that the meteorologists, when they give you the weather report in the morning, imagine they always are wrong. That means when they tell you it's not going to be rainy out tomorrow, then you should interpret that knowing that they're always wrong as I better bring my umbrella with me. Okay, so what we can see in this case here with our geologist, that's our coin toss geologist, he's only right 50% of the time. It is no matter if the signal is good or bad from them, the action that we're taking does not change. Okay. Furthermore, it doesn't change relative to what we did when we didn't have the geologist, right? With the geologist here, we're investing no matter what. And when we didn't have the geologist, the optimal action without the signal was also to invest, because our profit on average was 2 million, which was bigger than 0. So with our coin toss geologist, we were investing no matter what, right? He tells us there's oil, we invest. He tells us there's not, we invest. We don't listen to him. And that's exactly the same thing we were doing without the geologist. So if I'm taking the same action without the geologist as I am with the geologist, it has to be the case that the geologist is not valuable to me in this circumstance. It cannot possibly be. If they do not get my actions to change from at least some signal realization. Right? In the previous cases, there was value in helping us stay out when otherwise we wouldn't have. Okay, so the signal did not change our optimal action relative to what was optimal without the geologist signal being perceived by us. Therefore, it cannot possibly have any value in the sense that we've described, and we want to show that that is the case concretely here. Okay, so let's reduce our tree as we've done before, and we'll compute the value of information, recalling that after a good report, we would invest, we get 2 million, and after a bad report, we would invest, and we would get 2 million on average. So again, let's reduce that tree, plug in those values, and we should be able to take the same approach for computing the value of information we did in the last segment, where we're going to weight each of those tail values in green by their associated probabilities in blue. And you'll notice the weighted average of 2 and 2, a 50-50 average of 2 and 2, is just going to give us $2 million. And it should be no surprise that because that is the same expected payoff as what we got with no information, that the value of our coin flip geologist in this example is 0. Profit using the geologist was 2 million. Profit in the absence of the geologist was 2 million. And again, that was us doing the best we could in either case. Geologist does not help us improve our payoff in this case. Therefore, the value of them is even worse than it was when the signal quality was a little bit higher. Okay, so that is where I'd like to wrap this segment up. There is a little bit more advanced segment following that has you use Bayes' rule, and it goes through and solves the model that we're looking at by using a parameter P for the precision. In the last 3 segments, we looked at perfect information where we set P equal to 100%. We looked at an imperfect signal where the precision was 75%. That was where the geologist got it wrong 25% of the time. And in this segment, we just wrapped up with an example where the precision was 50%, P equals 0.5. That meant the geologist was essentially flipping a coin and would get it wrong just as often as they would get it correct. So with that, I will bid you farewell. Take care.